Okay, Calc 4, Lecture 13, continuing linear algebra. We discuss norm, dot product, and distance in Rn. Recall that Rn was the set of vectors like that, which are column vectors with n entries. We define norm of V to be like the generalization of magnitude of V in R2 and R3. So norm of V is this: V1 squared, V2 squared, up to Vn squared, square root. Now in R2, this is V1, this is V2, and this point has coordinates V1, V2, and we know that this vector is in fact identified with this point. And we see that the length of OA is this, and it's also norm of V, or magnitude of vector V. So using ideas from R2, we extend that idea into Rn, and we define norm of V. Sometimes they also call it magnitude of V in Rn, but norm is more, say, scientific, say, or mathematical or something. Okay, now if I have two vectors V and W, let me erase this. If I have two vectors V and W, we define dot product between these two. We define V dot W to be simply V transpose times W, or W transpose times V. No difference. So V dot W is defined to be transpose of this one is this times W will be V1 W1 plus V2 W2 up to Vn W. So that is dot product. Some of you who have taken Calc 3, you know this is like dot product for vectors in R3 or R2. Except we are using the language of matrices to define it. And I'm using this vector on top to emphasize that these are in fact vectors in Rn. Otherwise, they are basically matrices, right? So this transpose means the transpose of this as a matrix. Okay, now you can see that if I write this one here and this one here, it doesn't make any difference. I will get the same thing. So dot product will give me a real number. So when I dot two vectors, I will get a real number. And don't make that mistake. Well, at least I have seen like students in Calc 3, when they do dot product, they write it as a vector. No, when you multiply these, this one by this one, blah, 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 add them. That's the sum of those. Anyway, so that is the dot product. And let me define distance. And then write down some properties of these three things. Distance, okay, let's assume that we are in Rn. So this is Rn. Okay? And this is point O, well, Rn has point O, like the origin. And this is one point A, and this is point B in Rn. Now point A has coordinates v1, v2 up to Vn, and this one has coordinates W1, W2, up to Wn. Okay, now what is the distance between A and B in Rn? So the distance between A and B in Rn is very similar to distance formula in, say, it is a square root of this coordinate W1 minus V1 squared, W2 minus V2 squared, and up to Wn minus Vn squared. Now this is again extending the definition of distance. You see, well, in R2, right? Remember the distance formula in R2? If I have a point here which has coordinates V1 and V2, this B has coordinates W1 and W2, then the distance between A and B is simply from, say, college algebra, W1 minus V1 squared plus W2 minus V2 squared. And that comes from this fact that this is a right triangle here. We have a right triangle here, and this side of this right triangle has length V1. In fact, this is W1 minus V1, and this side has coordinate, this V2 is larger, so this side is V2 minus W2. When you square them, there's no difference between W1 minus V1 or V1 minus W1. So, by Pythagorean theorem, this happens. So, in fact, I have D squared. I have D squared equals this. Right? So, if I want D, I will remove this, and I have radical this. And since distance is positive, I will write the positive of this thing, not the negative. Okay, so extending this idea from, say, college algebra or geometry, whatever, we write this thing for distance between 2 points here. Now, this can also lead us to something else. Let me erase this thing and look at this more carefully. This looks like a norm of something. This looks like norm of something. Norm of what? Well, it has a W1 minus V1, W2 minus V2, so it is a vector with entries, these things. So it is a vector with these entries. W1 minus V1, W2 minus V2, Wn minus Vn. Okay, what is this vector? This vector is simply W minus V. Okay, so it's simply W minus V. So what we are doing is, in fact, finding the norm of this vector. So we just say distance between, so we define it to be distance between these two vectors to be this thing. We define distance between V and W to be the norm of W minus V. So this means distance between V and W, which in a sense means distance between the two endpoints. Okay, so these are the three definitions that I needed. Let me write them here. So V is basically square root of V1 squared up to Vn squared. Then the second one was W dot V or V dot W, no difference. They are the same. And that is V transpose times W as matrices. And the distance between V and W, which again is the same as the distance between W and V. You can see you can flip this thing and nothing happens because it is a square. And that is in fact W minus V, or it's also the same as V minus W. There is no difference. You see, again I say, if you flip this thing, when you square it, you will get the same thing. So that is the good thing about squaring something. So let me erase this and give you some properties of these three. One thing I should have said before starting this thing, in fact, we already have Rn, so we have defined Rn. Now we want to do something in this, say, space, like finding distances, for example, and measuring something. Not just adding vectors or subtracting or blah, blah, blah. No. We want to measure something. So these are like measurements, in fact. The norm and distance are measurements. And you can see that they're related. In fact, distance is defined using norm. Okay, let's see what properties I can come up with. Some simple ones and some more difficult ones. Some properties. What happens if I multiply that V by some scalar? So what is the norm of kV? Well, this k is multiplied by, so this is norm of what? This is norm of this vector, k v1, k v2 up to k vn. So it is a square root of k squared v1 squared up to kn squared vn squared. Sorry, what I was saying, is it okay? It's all k. So k is multiplied by all of them. I can factorize that k squared v1 squared the vn squared. So this k can come out of this radical, and we know when you bring this out, you put absolute value here. And so this is absolute value of k times norm of v. Okay, so that's absolute value of k times norm of v. Number two is, let's look at this thing again. Let's look at this and square it. So if I square this thing, I will get v1 squared plus v2 squared up to vn squared. Well, this looks like, you see that a dot product was v transpose w, and it was like v1 w1, v2 w2. So if I write this as v1 v1, v2 v2, and vn vn. So it looks like I'm dotting two vectors, one with coordinates v1, v2, v3 up to vn, another one again v1, v2, v3 up to vn. So this is in fact v transpose v, which is in fact v dot v. So norm is related to dot product in this way. So I can say that the norm of v is in fact the radical, it equals the radical of the norm. Okay. Another thing, this dot product can give me, it can be positive, negative, 0, whatever. But this one can't be 0 or can't be negative unless v is 0. Unless v is 0. So that is, in fact, another thing for norm. Norm is a number which is either it's bigger than 0 or it can be 0. So, but when is it 0? It is 0 if and only if v itself is a 0 vector. No other vector has norm 0. Why? If this is 0, then this is 0. If this is 0, then this is 0. Let me use another color. If this is 0, then this sum is 0. This is sum of some positive numbers, or let's say non-negative numbers. These are all non-negative. How could non-negative numbers add up to 0? To get 0, you have to add a positive and a negative number. So if you add non-negative numbers and you get 0, then all of them should be 0. If any of them is non-zero, then this sum is positive. So to have 0 here, all of them should be 0. All of them 0 means that this is 0. So the only vector with norm 0 is the 0 vector. And norm is, therefore, if we just ignore the 0 vector, norm is always a positive number. This also gives me something else here. If v and w are different points, then the distance between them is not 0. The only way that distance between two vectors is 0 is that when they are the same. The same means that w minus v is 0. So these things, they just extend to distance 2. So let me erase this. Let me check and see if an important object that we will see a lot is a unit vector. Unit vector. Oh, gee, I need this. Unit vector. A unit vector, as you from the name implies that it should have it should be related to 1. What 1? So we say that the U is a unit vector if it has norm 1. So U, if the norm of U is 1, then U is a unit vector. Then U is a unit vector. Okay, so let's look at some unit vectors in R2. And see how we can make unit vectors, how we can come up with unit vectors out of just any vector. So in R2, you probably remember from pre-calc the unit circle. Now, if I have a point on unit circle, this point has coordinates. Remember, if this is theta, this has coordinates cosine theta and sine theta. So this vector v has coordinate or entries cosine theta, sine theta. Okay, and I claim that this is a unit vector. Okay, well, we have to check its magnitude, or norm in this case. I mean, its magnitude in this case and norm. That is square root of cosine squared theta plus sine squared theta, which is equal to 1, which is 1. So norm of this vector is 1, no matter what theta is. So any point on the unit circle is related to a unit vector. So any point, in fact, as a vector is a unit vector. Well, examples of this are, say, if I have, say, let's say 60 degrees, for example. If I have 60 degrees, let me say if I have 60 here, then this point has coordinates. What are the coordinates? Let me, the square root of that's called square root is 1/2 and the square root of 3/2. So the vector u with these coordinates or these entries is a unit vector. And you can check, but the check is here because that this one is cosine 60 and this one is sine 60. And no matter what theta is, I will get 1. So any point on the unit circle gives me a unit vector. Now suppose I have any vector in R2, say. So let me erase this and I need some extra space here. So suppose I have let me draw the unit circle again and the coordinate axis. So suppose I have a vector like this, v, and with coordinates, say, a and b. That's okay, a and b. So if so this vector will be a and b. Okay. Now if I divide this vector or multiply it by its norm, so if I divide this by its norm, which means multiplying it by 1 over its norm, no, it's v, what happens? So I'm kind of dividing this vector by its norm. Let's see what the norm of this new vector is. This new vector, the norm of this new vector is simply, remember we had the property that we had, one of the properties that we had, k times u was absolute k times norm of u, right? So this is the norm of this thing times v. This is like k. This is a constant. So this will be absolute k and this is always positive. So it is 1 over this as k times norm of v. And I'm assuming that v is not 0. So this will be 1. So this vector has norm 1. So it is a unit vector. That's how you, given any vector, you can come up with a unit vector in the direction of that vector. So u is a unit vector in the direction of v. You can say that there's another one, which is if you put minus here. So there are 2 vectors. Now, what are they geometrically? Geometrically, when you do this, this one, when you use positive, this is in fact u. This is u. This whole thing is v, this is u. And this is minus u. Both of them are unit vectors in the direction of v. So these two, u and v, u and the minus u are unit vectors in the direction of V. Okay, but usually we choose the positive one. I'm not saying it is positive, but we will choose the one which is divided by a norm of V, not a minus norm of V. So just divide any vector by its norm, or let's say, because you might say, what do you mean with divide? You never define. Yeah, it means that multiply this by 1 over its norm. So 1 over norm of V times V is a unit vector. And this is the geometric form of it. Now in Rn, the same thing happens. This was in R2. So in R2, when we do this, we end up on the unit circle. Now in Rn, the same thing happens. So we can extend this idea to Rn, and in Rn we have something like a sphere, but we cannot really graph anything. So let's say that this is a unit sphere in Rn. So this is like Rn. And this is unit sphere in Rn. And I have something like this, point A, which has coordinates. Those are coordinates, okay. So this has coordinates v1, v2, vn, and then this gives me vector OA. Vector OA, in fact, is, let's call it V, and it is v1, v2, vn. Now, if I multiply this vector by its norm, this becomes a unit vector. Unit vector. Again, it is a unit vector in the direction of V, and if I do that, this vector, the endpoint of the vector is on this unit sphere. So this is U, and there's another one which goes this way, and minus U. Okay, so this is a unit we call N sphere. So circle in R2 is in fact unit 1 sphere. Let me see the R2 unit, so this should be N minus 1 sphere, because then in Rn, yeah, unit N minus 1 sphere, because it has N minus 1 dimension. N minus 1 sphere. Okay. And we write it as S N minus 1. Okay, so that's how you find unit vectors, and you will see how unit vectors become important in just everything that we study. In fact, unit vectors are like units of measurement. It's like the meter, for example. 1 meter, or 1 inch, or 1 foot, or 1 degree, say, Fahrenheit or Celsius or something. So that is the base. So unit vector gives me a base of, say, measuring something in this direction. Okay, so you will see how this thing works. So let me erase this thing. Okay, unit vector, and some properties of, say, dot product. We can see that properties of dot product. Properties of dot product is, first of all, you can see that the W dot V equals V dot W. I wrote it over there. And 2 is, I can remember them. So, then if I have U dot, say, V plus W, then it distributes over addition. So this is vector addition dot W, and 3, let me see what else we have. And so if I write K U dot V, it's like writing U dot KV, or just write K outside. Okay. The last one which I explained is in fact V dot V, which is in fact norm of V squared, is bigger than or equal to 0. And it is 0 if and only if V is 0. And remember I discussed this when I was telling you that norm is 0 if and only if the vector is 0 vector. So these are basic properties of the dot product. And well, let me see. Another one which I should have added here, so number 5 is, if I dot the 0 vector with anything, either way, I will get 0 number. Because it has 0 entries, so 0 times anything is 0, and you're adding zeros. So that is another one, but the most important one which you will see this in so many other areas of mathematics is this. Inequality. So that is the so if I have U and V vectors in Rn, then absolute U times V, or dot product, is less than equal to U V. Okay, so it means that if you dot these two vectors, U and V, dot them, and remember dot product can be positive or negative, so dot them and the absolute value of that, because if it is negative, then this is negative, this is positive, and it's obviously less than positive. So we put absolute value. Absolute value of this guy is less than the magnitude of this times the magnitude of this, or the norm of this times the norm of this. So this amazingly important, and it will come up in many areas of mathematics. So that's the Cauchy-Schwarz inequality. So let's see what we will see an implication here, a crucial implication, and so let me erase it and write it somewhere up here. Erase this thing because I don't want this thing. So the Cauchy-Schwarz inequality is U dot V is less than U times V. As numbers, these are just numbers, positive numbers. And this is a number, absolute value of that number is less than or equal to these two. Now, There are two other inequalities which I call them triangle inequalities. And one of them is this: u plus v norm is less than norm of u plus norm of v. Okay, I will show you in the picture. And the second one is a distance between, say, u and v is less than or equal to distance between u and w plus distance between w and v. Okay. Why triangle? Let's look at this one. If I have a u, this is a u, and this is a v, and this is u plus v, right? Maybe you have seen this in high school geometry, that the length of this plus the length of this is bigger than the length of the third side. So length of one side plus length of another side is bigger than the length of the third side. And that's it. So norm is like length. So length of this is less than length of this plus length of this. This is the same thing. This is in fact u, v, and w are now like points. So well, let's say u, w, v, w. So this should be w. U and v as points now. So this is this, this is this, and this is this. So it's saying that distance between these 2 points, which is the third side of this triangle, is less than distance between these two plus these two. And that's the same thing as that. And that's why it's called the triangle inequalities. So in 2 different ways, I mean 2 different ways of saying it, these are related. This is in fact a consequence of this first one. Now the first one is a consequence of the Cauchy-Schwarz inequality. So let me prove these 2 and then finish this lecture. So let me erase everything except this and try to come up with something. So I have u plus v. I want to say what I can do with this thing. So this, remember, I can write this thing, let's square it, I can write it as u plus v dot u plus v, right? U plus v dot u plus v. That was one of the things that we discovered. So, remember this? It was just for 1. Remember this thing? So it's the same thing. So it's like 1, it's this times itself. And we know that dot product can distribute. So this is in fact u dot u plus u dot v plus v dot u is like foiling it, v dot v. Now, this guy here is this. This one and this one are the same. You see, we can flip this thing. So we have 2u dot v. And this one is v squared. Okay. Now the Cauchy-Schwarz inequality tells me that this guy here with absolute value is less than this. So this basically is less than, well, this thing doesn't change, 2 times this. And this one doesn't change, right? Even with absolute value, this is less than this, let alone without absolute value. So, and this is what? This is from college algebra. We know that this is u plus v squared. Remember, u plus v squared is this one squared plus 2 twice this one times this one plus this one squared. Okay, so we have found that this is less than this, right? So let's bring it down here, and so we have u plus v squared is less than or equal to this. That's the end result, and since both of them are positive numbers, we can get rid of the square, the two squares, and we get the triangle inequality. And I said it comes from Cauchy-Schwarz. Okay, so that is the triangle inequality in this case. Okay. Now, what is the other one? The other one was about distance. So let me erase this thing. And the other one is distance between v, u and v. Well, let's write u first. So distance between u and v. So that is this thing. Remember, that was u minus v. I can write this thing in this form: u minus w plus w minus v, right? These two, they cancel out. So by the previous one, this is a vector plus another vector. So this is in fact less than equal to the norm of this plus norm of this. Okay, so and this guy here is in fact d of uw, and this is d of w and v. So we have proved that d of uv is less than equal to d of uw plus d of w and v. Okay, so I got the triangle inequality for you, and there are two other equalities. In fact, they're like identities that I'm not going to write them down here, and these are the basic ones that you need to know. And more than anything else, in fact, we will be using that unit vector. So it's good to have some practice on finding unit vectors. It's very simple, but anyway. So let me stop this lecture here, and I will continue with the next section.